Welcome to Complexity Made Simple. My name is Paul Allen, and before we get into today's video, well, I'm just going to remind you the 3 books that are on sale. Drink tea and read the paper. If you're a green belt and a black belt and you want simple instruction on how to apply your skill, design of experiments for 21st century engineers, and finally, a statistical process control for small batch production. They are all available from lulu.com and the links are in the video below. Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, well, this is an introduction to a presentation I made a couple of months ago to some engineers in Texas to introduce design of experiments to them. So you're going to see me talking to them a little bit. There's an email that I'm referring to and some people that I'm referring to. But when I watched the video back, I thought this is a nice video for people to see. It's an introduction to design of experiments. The people I'm presenting to are engineers. They're molding engineers. They're over in Texas. They typically make medical device moldings. So that was the group that I was talking to. So you're going to see that now. If you want more information about the sort of things I do, remember the books, drink tea and read the paper. Design of experiments. So this video is all about design of experiments. If you want more information, design of experiments for 21st century engineers. And finally, my latest book, Statistical Process Control for Small Batch Production. The links are in the comments below there, so you can go to Lulu and buy those books. That would be fantastic. But now, here's the video about introduction to design of experiments. Okay guys, let's start off then by talking about my assumptions whenever I'm talking about design of experiments. And I suppose some of those assumptions are actually in the phrase that I've got on the slide there, which is that for me, design of experiments is the fastest, most reliable way to get the most process knowledge. Okay, so that is my, it's my assumption, if you like. So one of the things I want to get across to you is my view is why any other technique you use is simply, I'm going to say simply useless. The way I describe design of experiments to my clients is like this. Design of experiments is like standing on the top of Mount Everest. But if I step in a single footstep in any other direction, boosh, I disappear down into the weeds 10,000 feet below. Design of experiments is simply the fastest way to learn the most. And to me it's easy, all right? So as far as I'm concerned, it's an easy thing. I teach design of experiments to operators. So I believe that operators can do DOEs. It's just not that difficult to do. So I need to explain my point of view of why it's the fastest, but I think we also need to just think about where the audience might be. So I asked Roger, I said, where do you think the audience might be on this? And he gave me this email reply. So this is Roger's quote. So I hope you don't mind me quoting your email, Roger. But here's what Roger said to me. So here it is. He said, many of the audience will have a manufacturing quality background, will have a good idea about DOE, even if they've never performed one. I suspect they have been influenced, though, like me, by past training that was so intense using a costly tool that not everyone has. It was quickly forgotten. The only thing that remains in the mind is something like, DOE is fantastic, but really hard. In my experience, when a significant problem is complex enough, they call in a consultant to do the work. The leadership hates that cost and the time of the trials. Okay, so part of my presentation this evening is to try and address what you've got on that quote. That DOE is really hard, it's quite intense to learn and things like that. That is true if I teach you all the mathematics. Let me tell you fellas, I left school at 16. I don't have that mathematical capability. I do DOEs all the time. Why can I do it? Because I press a button on some software that cost me $200. That's it. It cost me $200 to get the software to do this. Alright, so I just want to put that on the table to start off with. But let's talk about my assumptions, which are buried in that comment about it's the fastest, most reliable way to learn. Alright, so here we go. Let's talk about design of experiments. I'm actually just going to talk about doing experiments. I'm just going to talk about learning how your process works. Now, we're all engineers. Most of us are just engineers, guys, and we're all interested in bits of kit. We're interested in bits of machinery, and we like going up to bits of machinery and having a twiddle around. What does time do? What does temperature do? What does speed do? So let's start from that point of view, because if you don't do a DOE, that's your alternative, is that you walk up and that you make it up yourself. All right. Now then, if I walk up and I go, okay, temperature. All right, so I put the temperature to 120 degrees centigrade and I go, what does it do? And I collect a data point. All right, so there we go, collect a data point. What do you think? Is it telling me anything? Single data point? Nah, not really. Okay, so I need to collect some data. All right, so I go, okay. Let's say I collect 15 data points. I'm going to collect 15, all right? So, because if I collect 15, I'll start to see what's going on. I will see where the average is sitting. And I can see the spread, both of which are crucially important to what's going on. All right, so here we go. I've just done 15 data points and I've understood 120 degrees does. Okay, fantastic. But now I'm going, oh, okay, well that's interesting. I've landed there for 120 degrees. I wonder where I'd land if I set it at 140 degrees. So now I go 140 degrees. Of course, what have I got to do now? Well, I've got to do a similar thing. I've got to collect 15 data points. I've got to see where that thing's gone. Maybe I've made it narrower or wider. Have I moved the average some now? I get another distribution. By the way, it's another 15 data points. So 30 data points, and I've understood just one dial, and I've just understood these two places, and that's all. And this is my assumption. So my assumption is that if we're going to learn, we got to collect a reasonable amount of data. All right. So if we're going to learn, we're going to collect a reasonable amount of data. Now, I've just gone temperature, and I use 30 data points to figure out what temperature's up to, certainly within that window there. But you've got computer controlled machines with flipping heck, lots of adjustments on. So, you know, if you've got a money making process, you've got your money maker here. Let's say you got 7 variables. Now we took 30 data points to understand what that one variable did. Well, now look, I got 1, 2, 3, 4, 5, 6, 7. Now I need 210 data points. to understand what's going on. Now here's my point. So what I'm saying to you is, number one, reliable. I said the phrase, design of experiments is the fastest, most reliable way to do it. Reliability comes from the sample size. So to me, the sample size is a given. If you want to take 3 data points, then what you're doing is guessing. And if you're happy with guessing, that's cool with me. I can't stop you from guessing. But you've got to take a sample size to get reliability in your process knowledge. That's an assumption I'm making, okay? If you do that for every variable, you're going to end up with bucket loads of data, all right? So when you say in the thing there, the leadership don't want to pay for the cost of the trials, that's okay, guess. Because that's not painful at all, is it? That's not a problem at all, guessing. You always guess correctly, didn't you? You know, you wouldn't be all sitting here learning about design of experiments if your guessing was brilliant. You wouldn't need any other tool. So the assumption is we have a sample size, and we want to get process knowledge. And my other assumption about the process knowledge is this. When you set your machine up, and obviously you've got some outputs here, which you're interested in optimizing, my understanding isn't that you can find settings that work. I know you can do that. You wouldn't be in business if you couldn't make some of your settings work reasonably well, all right? Lowish defect rates. So I know you can do that. That isn't my point. My point is, I want to find the cheapest or the best settings. And that is what I'm talking about. Design of experiments. It's the fastest, it's the cheapest, it's the most reliable way of finding the answer. All right. So now I need to tell you how simple it is. Taking the maths to one side, I need to tell you how simple it is, so that maybe we can buy into the idea that this is a cheap, fantastic, brilliant way of learning how to make more money, because that's what I want you to take away from this workshop. Okay, so sticking with the idea for a second, that we're just going to understand one variable, and then we'll build it up into a designed experiment nice and quickly. We would all be comfortable with the idea of taking one variable, as I've done, temperature. So temp on the x-axis. Maybe we measure in, I'm just going to come up with something. Maybe you're measuring the effect of strength on your product, and that what you do is you make a number of tests and we build something up and we create a mathematical understanding of what's going on. Now, to be quite honest, this is something that I learned this when I was probably 15 years of age. So this is pretty basic mathematics, and of course the brilliant part about this is we can come up with an equation. So there's y going up there, there's x. So we can predict strength based on the temperature using a little bit of mathematics. Now the beauty of prediction is that in this case our scale only goes from 120 to 140. But imagine the scale was finer, imagine there was more choices, imagine this was more broad, and maybe there were 1,000 units on this scale. the beauty of what you're doing here is you're only having to test in a limited number of places. Then you can predict the rest. And that's the power of what we're doing here with this simple idea of inputs and outputs. Okay, so one input, one output, relatively straightforward. But here's where the problem gets really difficult. See, here look, we've only got what I would call a design space. You've got a design space of just 20 units here. But if you add more variables, so we talked about 7 variables. If each one of your 7 variables has 20 choices, each one has 20 choices, and we're going to take a look at an example in a moment. We'll have a look how many choices it's got. If you've got 20 choices for variable 1, 20 choices for variable 2, One, 2, 3, 4, 5, 6, 7. 2, 4, 8, 16, 32, 64, 128. What's that? I can't even work it out. There you go, 1.2. So if each variable that you play with, and you only have 7 variables, you have 1.28 billion ways of setting your machine up. Now, how are you going to find the best settings here? How are you going to find the best settings out of 1.28 billion choices that you've got? And this is just if the variables have got 20 choices. And by the way, it's just the variables, there's just 7 of them. There could be lots more than that, and there could be more on the scale than 20. This is a simple problem compared to probably what you deal with every day. So we want to be able to predict, because the power of prediction would be fantastic here, wouldn't it? If we could just do a small number of tests and the power of prediction. Well, that's what DOE does. It just does a small number of tests and allows you to predict the rest. So let's go back to our graph for a second. Look, I tested in multiple places here. But how many places did I need to test in, really, for a linear response? Well, because it's a straight line, I could have got away with just 2 points. And if I'm going to pick 2 points, which 2 points would I pick? Well, I'd go low and I'd go high, and I could predict the rest of that line. Very simple, isn't it? So let's just clear the board off a second so I can get a little bit more space, and we'll add some more variables to this diagram. Okay, so we just got one variable, one input, one output on the original diagram, and we tested in 2 places. We tested low and we tested high, and this was temperature. Low and high. But let's say you want to test another variable, let's call it time. Time. You test low, you test high. So now instead of testing in 2 places when we've got just one variable, what have I got to do? Well, I've got to test in 4 places. 1, 2, 3, 4. And if I test in those 4 places, what can I do with all the places I haven't been? In other words, inside this box here, what can I do? I can predict the rest. So if we went 20 by 20, what's that? That's 400. I've tested in 4 places, so I can predict. The other 396 I haven't been to. That's fast, isn't it? 4 tests to just predict the rest of the design space. Let's add another variable. Right, time, temperature, pressure. I'm going to test low, I'm going to test high. Now, 400, what is it, 8,000. It's gone to 8,000 combinations. How many places have I tested? Well, I've just tested 8 corners, and now I can predict the other 7,900. This is getting powerful, because if I add another one, it goes to 16,000 combinations. I'm only going to test 16 points. And what you're seeing here, this is what a DOE is. Look at it. What is it? It's just a pattern. And by the way, that is it. If you wanted a simple way to describe a designed experiment, it is a pattern to learn the most from your sample size. You have to do this. So you're going to do your sample size. So if you just say, well, okay, I'm going to test 30 times. Which 30? Where? Where should I test them? Which would tell me the most? Well, there's a pattern. And it's those 8 corners. And if you test in those 8 corners, they'll tell you the most about the process, because they allow you to predict the rest. And that's all a designed experiment is. It's the proper pattern to learn the most. And the maths, well, the maths is easy. I press buttons on a computer. It really is very straightforward. There is a little bit of technicality that you need to understand. But really, the first thing I want to get you to understand is this. I need to do a test. I need to get some knowledge. I'm going to have to do a sample size. Okay, 30, 50 data points. That's going to be quite expensive. Well, if I'm going to do 30 to 50 data points, I need to learn the most. I know what I'll do. I'll do a pattern that tells me the most for those 30 data points. But the 30 data points is a given. It can't be avoided. You can guess if you want, but I would sooner do the test properly and learn the most. So they're my assumptions. That's what DOE is. It's just a pattern to allow you to create a prediction equation so that you can predict every other combination. So literally I could go up to this design space and I could say, if I put pressure at this setting and I put time at this setting and I put temperature at this setting, somewhere where I've never been before, and I can't remember, there's no way I could know 8,000 settings. It'll tell me what the result will be. It'll tell me what the strength's going to be. It'll predict that. I don't have to carry it in my head. And that's the power of design of experiments. It is a pattern to learn the most and predict every combination that's of interest to you to hit the target that you want to hit. I don't know any other way to get that much information in such a short, cheap test. It's the cheapest way to find out.